right, we are on chapter 7, and this is section 1. So this chapter talks all about the states of matter and their attractive forces. So when we talk about this, we're going to talk about gases first, and gases are really important in the body. They're really important in terms of all of our respiratory system and how the gases dissolve, and so you have to understand the gases in order to understand that. And then we'll go on to the other states of matter, liquids and solids, and how they behave is all based on how they're attracted to one another. And so we'll go through that. And then we'll talk about how that attraction affects solubility, because a lot of things are soluble inside of our body, and how they're soluble is really important for how all those molecules interact. Then we'll talk about lipids, dietary lipids, and how they work. And then we'll talk about attractive forces in terms of the cell membrane. And I thought this was a really cool tip that your book had, and it said mix up your practice problems. When we do all the practice problems, we do them all in order. But when you're studying for the exams, what you can do is kind of skip around. So if you're in the back of the chapter book, if you're in the practice problems at the end of the chapter, you can kind of mix it up and go to all different numbers and try to do all different numbers in different orders, because that's what's going to be on the exam. And so I saw this tip and I thought that was a really good suggestion. All right, so first off, we're talking about gases and gas laws. So if you want to think about the gas laws, the first thing we're going to think about is pressure and volume. So let's say you have a syringe, and you have that syringe and you put nothing in it. It's got no needle in it. Hold on. All right, I found one. So like my kid had to take medicine, right? And so it's like give little kids medicine. But so what you can do is you can take this. It's got no syringe on the end. It's just a blunt tip. And so what you can do is if you put your finger over the end of it, right? Now, what's going to happen if I push down on the plunger? The air has no place to go because my finger's covering the hole, right? So I'm going to depress the plunger. What's happening to the air inside of the syringe? It's being compressed, and you get to a certain point where you can't press anymore. It's as compressed as it's going to get. And so what happens is that you're actually pushing the particles of gas closer and closer together, right? A sample of gas is mostly empty air. And so when you compress this syringe, hold on really tightly, when you compress the syringe, right, you're pushing those particles closer and closer together, right? And so what happens is that there's pressure. So if I decrease the volume inside of the syringe, what's going to happen? I'm going to increase the pressure. I don't know if you can hear it when I let it go, but you can hear the air come out because it was under high pressure. And so it all escapes out the end, right? And so our definition of pressure is a force exerted against a given area. So what force was me pushing down on the plunger, right? I had to keep my thumb on it, because if I don't keep my thumb on it, watch, right? If I don't keep my thumb pushing on the plunger on this end, what's going to happen, you'll see, I don't know if you'll be able to see, is that that syringe will come back. And so you actually get force against the walls of the container. And so that's what pressure really is. So hold on. All right, so when we measure pressure in a couple of different units. We measure in atmospheres, so ATM. So usually if you're at sea level, right, you're at 1 ATM. That's kind of an easy thing. The SI unit is not the ATM. The SI unit is the Pascal. And so you can look up here and you can see I've put all your conversions up here that you're going to need. And I believe all of these are on that, let's see, are they all on your back page? Yeah, they are. They are. Okay. So on your exam material, it's on that, but it's in the back of your book on the back cover. Okay, so 1 ATM is the same thing as 1,135 pascals, which is the same thing as 14.7 psi, which is the same thing as 760 milligrams of mercury. So all of those units, all of those units measure the same thing, which is pressure. So pounds per square inch, right? That's the amount of force per square inch of area, right? So pounds per square inch is probably one you've heard before. That's like, what's the PSI on your tires and stuff like that. That's kind of how we measure it in the US. Millimeters of mercury is used with a barometer, which measures the atmospheric pressure. And whenever we measure blood pressure for patients, you're actually going to use millimeters of mercury. And so the way this was initially measured is you have this tube, and this tube, it's like a test tube, and it's sitting in a dish. And so if you fill the tube and the dish with mercury, and you flip this tube over, right? Like you had it standing straight up, and then you flip it over into the liquid really quick. What's going to happen is that you're going to have some amount of pressure that the atmosphere is going to push on this liquid in this dish, right? And so what's happened is that the atmosphere will push the mercury up a certain height inside of the tube. And so how high up the mercury goes depends on the pressure in the atmosphere. And so if you're at sea level, it will rise 760 millimeters in height from the surface level of the dish. So that's where we get the 760 millimeters. And it doesn't matter how tall your tube gets, the mercury is only going to rise to 760 millimeters of Hg if you're at sea level. So that's how it was originally determined. All right, so let's try to do a little bit of conversions. Remember I told you conversions were not going away. I wasn't lying, conversions are not going away. So the first one, A, we're converting 1.08 ATM to millimeters of mercury. All right, so start with what you know. And then what you should have are all of your conversions. These are all in, like I said, the back of the book or the PDF that's on Moodle, that's your exam material, okay? So I know that in one ATM, and I'm gonna put ATM on the bottom because I want my units to cancel. In one ATM, I have 760 millimeters of mercury. So you don't have to memorize these, you just have to remember. So 1.8 times 760 gives me 820.8, but I know I'm gonna have to round that because I was given 3 significant figures, so I need only 3 significant figures. So when I round that, that is gonna be 8.21 millimeters of mercury. Okay. All right, B. B, we are starting with 750 points. So that's telling us that all of those digits are significant. Millimeters of Hg, and I'm trying to go to PSI. So if we look in our thing over here, we know PSI is right here. So we are starting with what? Millimeters of mercury, and we're going to PSI. So this is our conversion factor right here. So we have 760 millimeters of mercury for 14.7 PSI. So our millimeters of mercury cancel. So do 750 times 14.7, then divide by 760, and you should get 14.5 PSI. Then our last one, C, 0.94 ATM, and we want to go to PSI. Kind of got squashed down there. Okay, so I know I have 1 ATM. In this case, I'm going to use this conversion right here. So I have 1 ATM, I have 14.7 PSI. So my ATM cancels, and I do 0.94 times 14.7, and I get 13.818, but that's not the right number of sig figs. I only have 2. So that is going to give me 114 PSI. Okay. All right, so gases kind of all behave the same. No matter what they're composed of, they have very, very similar behavior. Not exactly the same, but very similar. And so we use one unified theory to explain how gases behave. And even though all gases aren't exactly the same, they apply to this theory, this kinetic molecular theory. And the closer that the gas's properties are to the kinetic molecular theory, we call it an ideal gas. So the more it conforms to the rules, the more ideal it is. So if you look at our ideal gas law, there are some assumptions. Gas particles are far apart from each other. And that's true, right? In gases, those molecules are the farthest away. If you compare them to solids and gases, right, those particles are really far away. So most of the volume of a gas is really empty space. We know that gas particles are moving a lot, right? They're in constant random motion, and they have a range of speeds. So the heavier something is, the faster it's going to go, right? And you can think about like a really big vehicle is really hard to stop because it's so big and it's going so fast, right? Gas particles, since they're so far apart, we assume that they have no attractive forces between them. And when gas particles are moving, right, remember we talked about temperature. Temperature is a measure of how fast the particles are moving. And we call that particle movement, we call that kinetic energy, right? Remember we said you can have potential and you can have kinetic. If you're sitting at the top of that hill and you're waiting to go down, you have potential energy. But if you are actually going down the hill, you're actually moving, that's kinetic energy. So because those gas particles are moving, they have kinetic energy. And that energy is proportional to the temperature. So the higher the temperature, the faster the particles move. And so these assumptions about gas behavior allow us to quantify relationships between all of our different factors that we can measure. So we can put it into a mathematical formula called the ideal gas law. The ideal gas law is pressure times volume is equal to N is number of moles of whatever gas you are. R is a gas constant, which you don't really have to worry about because if you need it, I'll give it to you, but right now we don't need it. And then T is temperature. So the way to remember this formula is in your book, and it will be on that form that you get with your exam, but it'll make your life a whole lot easier if you know this without having to look. So this is called PIV-NERT. So if you remember that, PIV-NERT, PV is equal to nRT, PIV-NERT. That will help you remember the formula because I want you to keep this formula in your mind the whole time we're in this section because it's really, really going to help you. So you'll see I kind of wrote it at the top over here. So gases and our gas laws. The relationship between the different things inside this formula are each called a separate law. But you can use this formula to remember the different laws, okay? So this is my trick. Your book doesn't tell you to do this, but this is my trick. So if we want to think about pressure and volume, if you look at this equation, move it down a little bit. So if you look at this equation, right, it's just a mathematical equation. So if we increase our pressure, if we know that pressure is going to increase, right? I take my syringe and I push down on that syringe. I'm putting pressure on all those gas particles. What's going to happen to the volume? Well, as I showed you, right, the more I push down, the more pressure I put on that syringe, the smaller the volume got in the syringe. So you can think about that, but all of our problems aren't going to be about syringes. So if you remember anything, right, that has to do with this, if we increase something on this side of the equation, then we're going to have to decrease something on this side of the equation. I'm sorry, I said that wrong. If we increase something on this side, if this side goes up, this side will go down, right? So if we increase pressure, then temperature is going to have to, I said that I did it wrong again. I gotta stop. Okay, if we change something on this side, so like if pressure or volume go up, then this side is equal to this side. So we have to continue that. We have to make the left side equal to the right side. And so if we increase P and V, or P or V, what's gonna happen is something on this side is going to have to also go up. So you can relate the different parts. Now, what if you have like pressure and volume? What if you change pressure and you want to know what happens to volume? Well, they're on the same side of the equation. So you can assume that all of this is going to stay the same. So if you have an increase in pressure, what's going to happen to volume? How is volume going to change? Well, if I want this side of the equation to still equal this side of the equation, then my volume is going to have to do the opposite as my pressure. So my volume is going to have to go down. And that's exactly what we saw. We increased pressure by pushing on the plunger. And so what happened to volume is that volume then went down. The opposite is true. If you decrease the pressure, right? Like I let off on the, see, remember when I'll do this again. When I cover the end of the syringe, let me open it up all the way. Okay. When I cover the end of the syringe and I push down, what's going to happen is I'm increasing that pressure. My volume's getting smaller. My volume's getting smaller. And now when I let go, you can see that that syringe bounced back. So I decreased the pressure when I let go, and therefore the volume increased. So which equals to an increase in volume. So they're inversely proportional to one another, right? And so this is called Boyles Law, because there was a chemist named Robert Boyle who made this discovery of this interaction. And so you do have to know whose law is what. And so this is how I remember, because I have to have a little story to make it easy to remember. So there was this guy, his name was Boyle, and he had a hot date. And so he was getting all decked out, really, you know, dressing up, and was really excited about his date. And then he went to go look in the mirror, right? He was going to like go brush his teeth, get ready for the date. And he looked in the mirror and he saw, oh my God, he has this big boil on his face. And he was just peeved. So peeved, so P and V are Boyle's Law. So he was really peeved that he had this boil on the side of his face. And so that's pressure and volume. Just a way to remember, because we're going to talk about quite a few different laws here. All right. So you can use this. You can use this to figure out what's going to happen comparing an initial to a final condition, right? So our initial condition here was that I was under very high pressure, right? I compressed my syringe. This is my initial, and this is my final, where my plunger has gone out. So we can use this to compare initial and final. But I want to show you something before we go into all the different laws and you're trying to memorize this stuff. What I want you to remember is that in this Pivnert, R is a constant. So it's never going to change. So you can kind of forget about it. N is the number of moles. A lot of times we keep the number of moles constant. So you can kind of forget about that unless they start talking about moles of something. So we're left with PV and T. So what you can do is you can compare the initial condition to the final condition. So if we want to put all of one condition on one side of an equation, what I'm going to have to do is I'm going to have to take that T and move it over to the other side of the equation. How do I move it over to the other side of the equation, right? If I have PV equal to T, what's going to happen? Well, I'm going to have to divide by T on both sides, right? So I get PV over T. And so what I can do is I can say this is the initial conditions, and they're going to be equal to the same arrangement, but at final conditions. Okay, and so the reason we can do this is because these three things here, PV over T, is equal to basically a constant. And so we can use this. Now, if you remember this right here, you can answer almost every single problem. So you have to remember PV is equal to nRT. That's one to remember, and then this one. So how do you remember this one? I always remember that I put my peas and vegetables on the table. PV over T, peas and vegetables on the table. If you can remember that, you can answer everything, okay? So this is kind of your book step by step. I'm not even gonna go over that because I like my way better, and I'm hoping that you do too. Okay, so when we read a problem like this, what you want to do is pick out initial and final conditions and figure out what to do. And so we're going to do these practice problems within the lecture, and then I'll create a separate video that has the regular practice problems in it, because there are so many and I don't want y'all taking forever. So, all right, so the lungs of a normal adult female hold 4.2 liters. So this is volume of 4.2 liters under typical atmospheric pressure. So pressure is 1 atm. If a diver holds her breath and dives to a depth of 5 meters and the pressure increases, ooh, okay, so that's telling me that I have a change. So these are the initial conditions. So let me write kind of on the side, initial. These are initial conditions, and then I'm going to kind of draw my line, and I'm going to say here are some final conditions. And so let's see what happens. The pressure final increases to 1.5 atm. What is the volume final of the lungs at this pressure? So we have an unknown. So remember your peas and vegetables on the table. Peas and vegetables on the table, okay? So I'm going to call this PI, VI, TI is equal to pressure final, volume final over temperature final. So in this, we weren't given any information about temperature. So you can assume that temperature was held constant. So I can just kind of scratch it out and not worry about it. And so in this way, you don't have to know which law you're using. You just use this combined gas law and go with it. It makes life simpler. Okay, so pressure initial was 1 atm. And I multiply that times my initial volume, which was 4.2 liters. And that equals to my pressure final, 1.5 atm, times my volume final, which we don't know what that is. That's still our unknown. So to get our final volume, we're going to have to divide by 1.5. Divide by 1.5. So what do we get? 1 times 4.2 divided by 1.5. What you should get is 2.8 liters. And so you had your lowest number of sig figs is 2, so your answer should be in 2. And my question to you is, does this make sense? So if you remember your gas law, PIV-NERT, right? What did we do? When we went from our initial to our final concentration, final condition, we increased our pressure, okay? So if I increase pressure, then what's gonna happen to volume? Well, this side of my equation didn't change. It was held constant. So if I increase pressure, in order to make pressure times volume equal to this other side of the equation, I have to do the opposite and I have to decrease it. So we're gonna scratch that out and we're gonna say volume drops. Is that true? Is that what happened? We went from 4.2 liters to 2.8 liters. Yes, so that's a really good way to check your work. Did you do it right? Okay. So there's a practical application for Boyles Law, and that's breathing. Every time you breathe in, your muscles inside your rib cage and your diaphragm, they all contract. And that causes the volume inside of your chest cavity to actually increase. And so the air pressure inside of your lungs, because we have increased our volume in our chest cavity, right? Our air pressure inside of our lungs is going to decrease. And because we have a low pressure inside of our lungs and a relatively high pressure out here in the atmosphere, right? What happens? Air rushes into my lungs and it equalizes the internal and external pressure. Now, when those muscles relax and I exhale, why am I exhaling? Well, the volume of my chest cavity actually decreased, which increased the pressure in my lungs, and our air flows out. So it's kind of easier to see in a picture, right? So upon inhalation, right, our rib muscles contract, our diaphragm contracts. And when your diaphragm's kind of like a dome, right? And so when your muscles contract, the dome kind of flattens And so that's how you increase the volume inside of your chest cavity, is that your diaphragm goes from being like this to being like this. And so you actually increase the volume in here. Then when your diaphragm relaxes, it shifts up and you get less volume. And so that forces the air out. So it's a practical application of that. All right, so let's try one more problem with Boyles Law. And it doesn't really matter. You don't have to know it's Boyles Law. Well, you do have to know Boyles Law, but to solve a mathematical problem, you don't have to know which law you're using. All right, so pilot undergoes altitude training. He starts his training at an atmospheric pressure of 762 millimeters of mercury, where his lungs hold 6 liters of air. So lungs hold, that's volume, 6 liters of air, okay? Let's see, he changes his altitude and his lungs expand to hold 6.25 liters of air. So we know that we're changing conditions. So this is my initial, and this is going to be my final. So I can call this PI, VI. So I know I'm going to have a pressure final and a final volume as well. So let's keep reading. What did it say? He changes altitude and his lungs expand to hold 6.25 liters of air. What's happening to the atmospheric pressure in millimeters of Hg? All right, so all you have to remember is to keep those peas and vegetables on the table. Peas and vegetables on the table. So this is my initial. Here's my final. Okay, so now what's held constant? Temperature's held constant. I can just cross it out. So my pressure initial is 762 millimeters mercury. My volume is 6.0 liters, equal to my pressure final, which I don't know, times 6.25 liters, that's my volume. Okay, so what do I do to get pressure by itself? Divide by 6.25 liters, divide by 6.25 liters, and we get a pressure final of, what you should have gotten was 7.32 millimeters of mercury. 732, I think, not 0.2. I think I wrote that wrong. 732. Okay, so does this make sense, right? Let's think about our PIV NERT. PV equals nRT. What did we do? What did we change? See our volume here. What happened to our volume? Our volume went up. Whoa, our volume went up. And so to keep this side of the equation equal to this side of the equation, if our volume goes up, what happens to our pressure? Pressure has to go the opposite. Pressure has to go down, okay? So did that happen? We went from 762, right, to 732, and so it did. So we're good. It's just a good check, just to make sure you're on the right track. All right, the next one is Charles's law, and Charles's law relates temperature and volume. And so when I think about Charles's law, I do think about my son because he's Charles, but that's not, and that's not why I named him that, FYI. It was my grandfather's name. So family name, not a, not a science name. But when I think about Charles's law, I think about different television shows. Y'all are probably too young, but I watched Charles in Charge, right? That one. Charlie's Angels. You know, so that's what I think of. I think of TV and Charles's Law. So TV shows with Charles in it. That's just how I remember. All right, so he was the one who figured out there's a relationship between temperature and volume. If you make things cold, like look here at this balloon, right? We're gonna blow it up, and then you take it and you put it into a cooler that has ice in it, right? What's gonna happen? The temperature of that gas inside the balloon is gonna decrease. Well, if the temperature decreases, look at that balloon. Now it's all like wrinkly, right? The volume decreases. Well, does that make sense with PIV NERT? PV is equal to nRT. So what do? We decrease the temperature. If we decrease the temperature and I still want this side of my equation to equal this side of my equation, what am I going to have to do? Well, if I decrease one side, I have to decrease the other side. So what's going to happen is that my volume is going to decrease. Okay. So the same is true as if I heat the balloon. If I heat the balloon, temperature is going to go up. What's going to happen to volume? Volume's going to go up and it'll probably pop, right? Okay, so we're not going to go through their rules. We're going to use our rules. So we have to remember piv nert, and we have to remember our peas and vegetables on the table. So 2 things. Okay, if you remove a balloon with a volume of 105 milliliters of air from a freezer that is at a temperature of 0 degrees Celsius. Now, before we do our work, there's one thing you have to remember. Always convert temperature to Kelvin. That is the only way this stuff works. You must convert to Kelvin. So plus 273, and I do believe that this is in the back of your book. Let's see, yeah, under temperature, they'll show you just add 273 degrees Celsius and you get Kelvin, so that's 273 Kelvin. Let's move this over. Okay, so this is our initial, and then we're gonna see what happens. What happens, let's read. We want to warm the balloon to room temperature of 25 degrees Celsius. What's the volume? So volume final is our unknown. Temperature final is 25 degrees Celsius. Make sure you convert that to by adding 273. And so you should get a temperature of 298 Kelvin. All right, so now peas and vegetables on the table, right? Initial, peas and vegetables, but these are our final peas and vegetables on the final table. Okay, now what's held constant? They didn't tell us anything, this is our final. They didn't tell us anything about pressure, so you can assume pressure was held constant. So now all we're worrying about are volume and temperature. So if our volume initial is 105 milliliters, and our temperature initial was 273 Kelvin. Our final volume is unknown, and we have 298 Kelvin. So what do we have to do? Hold on. All right, so what do we have to do? We have to multiply times 298, multiply times 298. So our volume final is 298 times 105 divided by 273. You should get a final volume of 114 milliliters. So does it make sense with piv nert? Always go back and double check. Does it work? Okay, so if we look at our temperature, what happened to our temperature when we went from initial to final? We increased our temperature. If you're going to increase your temperature, what is going to happen to your volume? Well, if we increase something on this side, we have to increase something on this side. So it should be an increase in volume. We went from 105 to 114. We have an increase. So it's just a good double check. Did you do it right? All right, temperature and pressure. This is Boyles Law. I don't actually have one for this one. It's kind of like the only one that doesn't have one. So it's temperature and pressure. All right, so when our temperature increases, our gas particles are gonna move faster, right? And think about when things move faster, we talked about in chemical reactions, they have more collisions with each other. Well, not only do they have more collisions with each other, but if they're inside of a container, they're gonna have more collisions with the sides of the container. So if you increase temperature, you're gonna increase pressure because they're striking the wall more. And that's the definition of pressure. Pressure is how frequently particles will strike the walls of a container. And so how did he get this? How did we get this temperature and final? Remember, peas and vegetables on the table, right? Peas and vegetables on the table. And so if we just want to talk about pressure and temperature, we just get rid of volume. And we say initial, final. We have the law, right? So just remember your peas and vegetables on the table and you're going to be good. And the same thing's true about piv nert, right? So what happens if you increase the temperature? Well, if you increase something on this side, what are you going to do? You're going to increase something on this side. So you can have an increase in pressure. It's just a good way to double check, right? Okay, so you can combine Charles's law, Boyle's law, Gay-Lussac's law into a single gas law. So this is the combined gas law, and you've been using it the whole time, right? So the only thing is that you have to have the same amount of gas, because remember this comes from PV and RT, and we said R is a constant. And so a lot of times we hold the number of moles of a gas constant, ES, constant. And so if we do that, we can basically say, okay, those are going to stay here. These are going to be a constant, and I want to move T over. So I'm going to divide by T, divide by T. I get PV over T is equal to a constant, right? And that's why we can do this. All right. And we've been using this the whole time, so we're ahead of the game. All right. So we have a 1.20 liter sample. That's my volume of an ideal gas at 30 degrees Celsius. Okay, 30 degrees Celsius. I need to convert this. I put 30 degrees Celsius. I need to convert it. So plus 273 gives me 303 Kelvin. Okay. And 1 ATM, pressure is 1 ATM. And it's 0, 0. So we have 3 sig figs there. Okay, it's heated to. Oh, we changed it. So this is our initial. Here's our final. So what do we get for final? Is heated to. We have to have a volume, a temperature, and a pressure. So our volume, oh, I'm sorry, temperature is heated to 225 degrees Celsius plus 273. So that would give us 498 Kelvin. And then what do we say? A pressure of 1.5 ATM, and then a volume. Oh, we don't know. What is the final volume? We don't know. So just do your peas and vegetables on the table. Initial, final. Okay, and in this one, you just don't get rid of anything because we're changing temperature, we're changing pressure, and we want to know what happens to volume. So you just don't cross anything out. Just plug it all in. So our initial pressure was 1.00 ATM. Our initial volume was 1.20 liters. We know our temperature, 3.03 Kelvin. Okay, our pressure final was 1.5 ATM. Our volume final is unknown, and our temperature final was 498 Kelvin. Okay, so what do we do to get rid of things? You're just going to cross multiply. So that's 498 Kelvin on top and 1.5 ATM on the bottom. Okay, so volume final, because that will get rid of those, right? So do 498 times 1 times 1.20, and that is a liter, not a 2, because that kind of looks like a 2, but that's liters. Then divide by 1.5, and then hit enter, and then divide again by 303. Or you can put things in parentheses, but just don't make a calculator error on here. So double check that you know how to do this on your calculator. You get, 1.31 liters. Okay. All right. So, and your book says this at the end, and I think you need this in the beginning, but know your ideal gas law. If you know your ideal gas law, and you know this is your combined gas law, you're good. So you got to remember PIV-NERT, PV is equal to nRT, and then remember peas and vegetables on the table, and you're good. Okay, so this is kind of your summary slide. I put everything together. So remember Boyle's Law, he was the one who was peeved that he had a boil on his face. Charles's Law is TV, so temperature and volume. Gay-Lussac is just what's left over, pressure and temperature. And then combined gas law is all of them, okay? And that's it. So I'm gonna do a separate video that has the odd practice problems in it.